Hi, welcome to Holyfield Physics TV. Today we're going to look at the magnetic effect on electric currents, and this is part of the OCR Physics A2 course, Fields, Particles and Frontiers of Physics. The direction of the field and the current and the force experienced are all perpendicular to each other. And to figure out which is which, we use Fleming's left-hand rule. So we have our thumb, first finger and middle finger all at right angles. First finger is the field, second finger is the direction of the current, and the thumb is the direction of motion of the conductor. As you can see, all at right angles to each other. It's like an X, Y, Z graph. Now if we have a nice uniform magnetic field flowing left to right on the screen, it means the North Pole is on the left and the South Pole is on the right. So we've got our field to the right. Into that field we put a conductor, pass a current through the conductor, current value I. So the current is into the board, into the screen. And that gives us, with Fleming's left-hand rule, a downward motion, a downward force. If we have alternating current, we get the conductor to oscillate, depending on the frequency of the AC. Current flows backwards and forwards, so the force is up, then down, then up, then down. If we have the right conditions, we can set up a standing wave. So there's the fundamental mode of our standing wave. And the factors that are going to affect that are the frequency, strength of the field, the flux density, and the mass stroke tension of the conductor. So it's the mass per unit length and also possibly the tension, the weight that we have hanging on the conductor. And as our B field is to the right, pass a current through that B field. This one's coming out of the board, out of the screen, and we get an anti-clockwise field using the right hand thumb rule. These two fields combine, and this is what causes the force. And so the effect we have is that the field is stronger under the wire. This gives us the force upwards. Now to look at the size of the force, it's going to be proportional to the two fields that are just combined with each other. And those two things are to do with the flux density and the size of the current. But the other important thing is the length of the conductor that's in the field. And we get the magnetic force FB equals BIL. F equals Bill. But left hand's rule, everything's got to be perpendicular. So we need to put a sine theta into this. So our final equation is F equals BIL sine theta. And if we look at a single electron, our wire is full of electrons. When we apply a PD to this, all of the electrons move together, and that's what we've got as an electric current. The force actually is determined by each individual electron. So let's look at a single electron. It's moving to the right, so it has a velocity v to the right. Remember that the electron is negative though, so our conventional current I is to the left. As it moves through the B field, it's going to experience a force because the electron is the electric current. So we have F equals BIL, but we know that I equals charge over time, so F equals BQL over T. L over T is the velocity. So we now have, for a single charged particle, the magnetic force acting on it, BQV sine theta. So just to recap, there are the three important things from this session. We've got Fleming's left-hand rule, we've got the force on current carrying conductors, and we've got the force on moving charged particles. You've been watching Holyfield Physics TV. My name's Richard Gould. Thanks a lot for watching and listening. Work hard, do well in your exams.